Hello, my name is Pani. I'm a master's student from the University of Alberta, and today I'm going to present a work that was published in IEEE Robotics and Automation Letters. This work is focused on deep learning methods for myoelectric control of robotic exoskeletons. In my case, it's specifically for upper limb exoskeletons. The main motivation of this work is preventing injury of workers in industrial settings and ensuring their safety while they're performing repetitive tasks that needs augmented support in load-bearing situations. This will result in reducing fatigue while we are providing them support and stabilization while they're performing these tasks. This is the main structure of the system. I'm going to start with the user interaction with the hardware, which is the exoskeleton, and then moving forward to the other components of the system later. So the hardware is comprised of these artificial McGibbon muscles that are responsible for moving the joints of the exoskeleton using air pressure while being connected by cables and pulleys to these joints. All the parts in this exoskeleton are 3D printed, which makes it very lightweight. We have 3 degrees of freedom, 2 at the shoulder level, 1 for extension and flexion, and the other one for abduction and adduction. And the last joint is at the elbow. We have 2 Arduinos responsible for controlling the pneumatic actuators and also receiving angular position information from our encoders located at each level of degree of freedom. Moving on to the next component of the system, which is the main one. This is the end-to-end deep learning model that connects the multi-channel input of the EMG to the desired position of the robot, which is the future angular position. This deep learning model is comprised of convolutional neural networks and long short-term memory for capturing spatial and temporal features of the multi-dimensional EMG input. We used 60 millisecond windows of input with 2 millisecond sampling rate to predict 450 milliseconds of angular position into the future. The convolutional layers are comprised of 2 layers, each one followed by a ReLU, activation function, pooling, and batch normalization. We had 1 layer of LSTM with 50 hidden units, and at the end, we concatenated the CNN output and the LSTM output and then fed it to a fully connected layer comprising of 50 neurons. And then it resulted in a 3-dimensional output for each joint of the robot. After feeding it through a safety check process, we then have the desired desired position of the robot that we want to follow using our controller, which is a proportional derivative controller and a feed-forwarded gravity compensation. Our gravity compensation model was a modified version of a nominal model using neural network. We extracted this nominal model using a motion equation of the robot by zeroing the inertia matrix and the Coriolis matrix and resulting in a gravity matrix, which is the nominal gravity compensation model of the system. And then we modified this gravity compensation model using neural networks. We then feed forwarded this model to a fine-tuned PD position controller that has a proportional gain and a derivative gain, and then we have our control law. We evaluated the system by the help of 2 participants. These participants were instructed to follow 3 reference trajectories that was shown to them on a computer screen, and they were instructed to not exceed these boundaries, which is like a 2 centimeter radius of the reference trajectory. They were instructed to follow these trajectories using 3 speed modes and 3 different weight loads, which results in 9 different scenarios in 3 conditions, which are no exoskeleton at all, 1 with gravity compensation only, and the 3 using our deep learning model. They were instructed to do this in 2 postures, while standing or while seated. We also incorporated variations in electrode placement and breaks and pauses during the experiments. The results show a significant decrease in muscle effort from the users compared to in the IBPA, or intention-based predictive assistance method, which is our deep learning method, compared with no exoskeleton condition or only gravity compensation condition in all scenarios and all the trajectories, reference trajectories. We also showed an increase in the exertion of the torque from the robotic exoskeleton in these scenarios and trajectories. At the end, we showed that we were able to predict the future 450 milliseconds into the future while being robust to different variations in load, speed, and trajectories. We were able to counteract the effect of noise and sensor displacement and fatigue in the short term. On average, we saw a 48% reduction in muscle effort from the user and a 21% increase in the torque exerted from the exoskeleton. In the video here, you can see that the exerted torque from the exoskeleton is divided proportionally between the 3 joints of the exoskeleton, which is proportional to the intention that is coming from the muscles of the user. In the future, we want to personalize this process by using maybe model agnostic mental learning methods, because we saw that this model requires lots of data, lots of training for each individual each time. We also want to incorporate longer sequences for input, and also we want to predict longer sequences as the output. We saw that our system lacks the ability to handle heavier loads than 3 kilograms. So we want to also apply hardware components that are able to apply more effort than 40 Newton meters. We also want to incorporate methods such as attention mechanism that are able to increase the modularity of our system, and we could have less sensitiveness to the sensor noise, or even we could have robustness to sensor malfunctions. Now this wraps up my presentation, and thank you for your attention.